Hi everyone, and welcome to another Memgraph community call. Glad to have you all here with us. So today we have Dr. Tom Ganz joining us. He will be presenting a talk on topic graph-based vulnerability discovery. But just to give a short intro, I met Tom while he was doing his PhD research, and he was doing it actually on this topic. So that's how I met him. So he'll show you how to use patch-based static analyzers, while Memgraph is the backbone for data mining. I thought this will be a really interesting presentation, and I'd like to take this opportunity to thank Tom to join the community call and tell you more about us. I feel he will give you a really good overview of this. Although you might be not familiar with the topic, I think he'll still give you an insight into this not that easy topic, I would say. Yeah, just to give you also a bit of information about the community call, you can have a chat at chat tab, logically, and I see you're already doing that, so hi to everyone. If you have questions during this call, please post them in the questions tab, and after the call, I can read them out loud. And please make sure to post it during the call, so because it's hard once it's ended, I may not see all of the questions. Also, there will be a couple of polls posted, so if you can, please answer them. And I see we have a question. Yes, you will have the recording after the call, and it will be emailed to you if you register for the event. I think that's it. Tom, enough me. Please join the stage, and the stage is yours, and good luck with the presentation.
Thank you so much, Katerina. And thank you so much to everyone who joins this community call, and especially to joining my talk about graph-based vulnerability discovery, which was actually part of my PhD thesis. So my name is Tom. I did my PhD in machine learning and software security at the Technical University of Berlin. I have some past industry experience as machine learning engineer and security engineer at, for example, Volkswagen AG. And I worked as a security researcher at SAP from 2020 to 2024. And my research focus was vector detection, web application security, privacy for machine learning, and software security with AI, which is kind of the domain of this talk. And now I'm a security engineer at Amazon, where I try to mitigate ad fraud and do some network traffic analysis. Now, let's start straight away with why is this talk interesting? Why do we need this talk? And the thing is, there has been a massive proliferation of security vulnerabilities in the past or so years. As you can see, it is depicted on the plot on the left. And the number of disclosed security vulnerabilities is alarming. And the reason for this is, I guess, because writing software is kind of easy, but writing secure software is kind of hard. Having more software leads to having more bugs, and more bugs increase the likelihood of having more security vulnerabilities. We all have seen like the news covering zero-day exploits, vulnerabilities. I think you can all remember the CrowdStrike bug from 2 weeks ago. And luckily, there are tools to assist developers mitigating, introducing bugs and security vulnerabilities into their productive code. Those static analysis or static analysis security testing tools, as they are called, try to automatically infer a property of your code, in this case, whether the code is vulnerable or it contains a bug or not. And those tools are already vastly available. However, they all perform very different. We can see on the, as depicted on the plot on the left, that some tools even have an extremely high false positive rate. Some have a low detection rate, and assessing each false positive manually is extremely costly. It costs engineering hours. And the question is, why do they differ so much in their performance? And for this, to answer this question, we want to have a look on a false positive, on two false positives actually. On the left and on the right, there are two code samples. The right one from the Linux kernel, on the left, and the left one a pretty basic code snippet. And we analyzed it with a Clang analyzer, which is a pretty available, free static analyzer for C and C++ code. And on the left, it says we are dealing with a division by zero bug. However, if you look closely, it's not because the variable x being initialized to zero, but because we could potentially have the length equaling zero, then x is zero as well. And the problem is, if this method will never be called with length equal to zero, then we are actually not dealing with a division by zero bug in this case. On the right side, it's a bit more sophisticated. Here, Clang Analyzer says that the new hash pointer is not being freed, which is wrong because we are calling free ftrace hash on this new hash pointer. And the thing is, Clang Analyzer doesn't know the free ftrace hash function. It only knows the standard C library free function call, which has been like wrapped in this library custom function. And in both, the problem is that a static analyzer has too little context. We would need to give them more context about, for example, the free ftrace hash function or how this function foo is being called. So in my PhD thesis, I like to categorize like static analyzers into three broad categories, like that is a bit resembling the Chomsky hierarchy. We have those very easy static analyzers. These are the lexical analyzers, which just try to match tokens in the code to infer or deduce whether the code is vulnerable or not. Then we have the syntactic analysis, which is a bit more sophisticated. Those are actually doing some kind of parsing and work on the abstract syntax tree. And then we have the more or less state-of-the-art semantic analysis that actually try to infer data and control flow and see if a bug is actually reachable or not. So a static analyzer actually is just looking at source code without executing it. That means we have to either over-approximate the semantics of the program or under-approximate the semantics of a program. We cannot really approximate the semantics because we would have to execute the program code, which we are not doing because we want to have a fast analysis. And here's the thing: we cannot be at the same time complete and sound. Soundness of a static analyzer means that everything that a static analyzer says, like reports, is actually true. By completeness means that the static analyzer was able to find every bug that is actually present in the code, and we cannot have both. And I'd like to give you the proof, even though you would say this might be complex, but there is a proof why like a static analyzer can never be perfect. And that's due to the Rye theorem, which, and I quote here, Rye theorem asserts that it is impossible to decide a property of programs which depend only on the semantics, not on the syntax, unless the property is trivial. So how can we now prove that it's not possible to create a optimal static analyzer? Well, first of all, is the inferring a bug trivial? No, because there are buggy programs and there are clean programs. So is it only depending on the syntax? I would say no, because a bug, like a security vulnerability, most of the time depends on the input that is given by the user. So now, how do we prove that it's not possible to come up with a perfect static analyzer? And the thing that computer scientists really like to do is reducing it, like showing it's undecidable by reducing it to the halting problem. Which I hope you're kind of familiar at this point, because I hope you're a computer scientist just like me. And if we would now consider an optimal static analysis program, we could use it as an oracle to tell whether a program terminates or not by placing a bug after a legitimate program, and then asking a static analyzer if the bug is reachable or not. And this is a contradiction. So a static analyzer can never be perfect, and in this case, it can never be 100% sound and complete at the same time. But could maybe machine learning help us a little bit with that? I mean, we have proven that it's not possible, but maybe machine learning can still give us a better balance between soundness and completeness. And the answer is yes, because instead of manual crafting rules, the machine learning model could just learn them, and we can apply thresholds to them. If we kind of squint our eyes, soundness is much more like a precision, actually. And the completeness can be kind of calculated by the recall. And we can calculate the balance with the F1 score, which is just the harmonic mean between those two. And it turns out that from a work by Su et al. From 2019, that machine learning models actually beat or outperform static analyzers, like the simple ones at least, as we can see on the right plot. Here we see that some simple convolutional neural network or bi-LSTM was able to outperform like battle-proven static analyzers like CPP check or flaw finder. So, but before we get to some more improvements to this, I want to dig a little bit deeper to the fundamentals. And since we are here at Memgraph, we have to start with some graphs, right? And all of those static analyzers are working on like semantic graph representations of the program code, because like a static analyzer just on the code, like working on the code itself, would be too bloated, and a graph is much more concise and keeping the needed information to infer the rules we are interested in. So here's, for example, such a graph depicted in a program. This is the code property graph, which is from Yamaguchi et al. From 2014. And we can see it consists of the node from the abstract syntax tree, which is given to us by the compiler, the control flow graph, and the program dependency graph. But this is state of the art, actually, but I want to use another graph, which is the code composite graph. This uses the control flow and data flow graph and the nodes from the abstract syntax tree. This makes it much easier to handle because we're talking about flow, like the flow of a variable. Does one variable flow to another variable and so on, instead of dependencies, which makes our later analysis much easier, as you will see. The question is now, how do we use these graphs? How can we do some kind of static analysis on these graphs? And it is state of the art for rule-based static analysis that we kind of describe vulnerabilities in terms of graph traverses. That a traverse is kind of how do we navigate through this graph, and a traverse is simply a function that maps a power set of nodes to another power set of nodes. And then we can kind of define primitive operations like filtering nodes on this graph by some predicate B, for example. If some node fulfills this predicate B, then it is in our result set. We could also like query give us the immediate neighborhood of a node. And this is the out operation. And we can simply compose new function by just combining the primitive operations. For example, on the bottom, we see a example rule to detect actually format string vulnerabilities, like really easy ones, of course, but just to give you a glance how it could look like. For example, we can filter for user input nodes, take the neighborhood, see if they are flowing to some variable declaration, and seeing if this is the only declaration flowing into some printf method call. And if it is, then it could likely be a format string vulnerability, right? So, and such rules are typically handcrafted and implemented on some kind of highly efficient graph database. Now, my question is, can a machine learning model actually learn such rules? And before we do this, machine learning models need their data to be like their input feature space to be some kind of numerically represented. Like we have to embed the source code of the program into some actual Euclidean space, into some kind of vector space. And the most state-of-the-art method for doing this is kind of splitting the source code into tokens and then giving it some kind of numerical representation. in this case, Su et al. From 2019 use a skipgram model, which is called word2vec, and embed like the context of each symbol into some representation, and then average it over each symbol within a node, just to give a numerical representation for it. Because unfortunately, machine learning models are seldom able to work on textual information. Having this, we need some kind of way to kind of tell whether a program is vulnerable or not. Since, well, machine learning models are not able to like grasp graphs on their end, we have to kind of also represent each graph as some kind of numerical vector representation. And here's the thing: graph neural networks are perfectly like fit for this task. If we start with some initial feature space representation of our nodes, like we did in the previous slide, we could now go ahead and update each node's feature set according to the context where the node is in, like the immediate neighborhood. And a graph neural network is consists most of the time of an aggregation method, which kind of aggregates the information of the neighborhood of a node with itself, and then an update function, which kind of updates the feature representation of each node. And doing this, like in some hierarchical manner, we can like learn a representation for a graph in a Euclidean space, and then we can kind of easily separate it in the space for example, 1 for a vulnerable program or 0 for a clean program. And the most simple graph neural network is just a graph convolution defined by Kipf et al., where we kind of start with our initial node representation, and then we update it n times, depends on how many layers you want. And it's pretty simple. We just multiply the adjacency matrix of the graph to the left to your feature representation from the last layer. And then we just put it into some kind of multi-layer perceptron, where we just like multiply a weight matrix to the right and a sigma layer to get some nonlinearities. And if we combine this complete thing, like all these steps, then we have pretty much a state-of-the-art machine learning-based static analyzer, which can tell whether a program is vulnerable or not. And most of the time it works just like I told you. We collect some vulnerable and clean programs, for example, by crawling GitHub or by crawling some kind of vulnerability database. Then we transform it into some kind of graph, in this case, the code composite graph. We encode each node into some kind of vector representation. Then we put it through a graph neural network. And then we use some kind of prediction head, for example, multi-layer perceptron, which just returns either 0 or 1, whether the program is vulnerable or not. And that's it. There's some problems, unfortunately. First of all, the data is kind of limited. It's really like vulnerable programs are sparsely available because no one wants to publish vulnerable programs, of course. And even worse so, the context of these models is very limited. They only take like functions and then predict or infer whether this is vulnerable or clean, just a function. So there's context missing. This is just the inter-procedural analysis, we would say. This is not really the taint analysis I showed you previously, right? So the question is, can we actually have a machine learning model that learns such path, like a signature, how to traverse the graph in form of some kind of path? And this was my idea, actually. Can we like classify path instead of functions? Just like in taint analysis, we are not working with functions in taint analysis, but path. And what is a path, actually? A vulnerable path must be between like a user-controlled source and some kind of potentially dangerous sink. For example, memcopy or some kind of memory operation. And we want to have a graph neural network trained in such a supervised manner on those paths. And the first question was to me was, what is a source and what is a sink? A source could be like some kind of fixed programming language dependent set, for example, all user input functions, cin for C++, gets, fread, and the same for the sinks. For example, we could use memcopy, printf, memset, free, and then we would just like build a large graph of the program and see, can we find a path between all our sources and sinks, and we want just to have those in our training set. Other papers use, for example, also arithmetic expressions, pointer usages, array indexing, and such stuff, which would, for example, for FFmpeg, open source tool, this would be 16% of all statements marked as kind of dangerous. So one of the problems is here, finding all simple paths, I mean non-cyclic path between two nodes in a graph is an exponential time problem, because the number of paths in a graph exponentially depend on the number of nodes. So finding a solution is obviously taking exponential time depending on number of nodes on the edges. So the question is it maybe NP? Would it be that we can maybe just use some heuristic algorithm? Unfortunately not, because if we have a solution, it would take us exponential time again to prove whether this is actually a solution. So the only like reasonable way to do this would be probabilistic sampling, like give us only 10,000 random paths and we are done. The next problem is, how can we even store this, and what should we use? What database should we use? One of the state-of-the-art graph database tools to this time was Neo4j, which is written in some kind of JVM language, if I'm not wrong. But we wanted to have something faster, some kind of in-memory database, and Memgraph was, in our benchmarks, the best compared to Neo4j and Redis Graph. It was almost 100 times faster than Neo4j. That's why we stick like kind of to Memgraph. Also, it had some pretty nice UI where we could easily get a security engineer on it and say, here, try some queries and see if you find a vulnerability using this Memgraph UI. Here's an example of it, for example, where we have a vulnerability found, actually a vulnerability in libxml2. So anyway, for the training of the machine learning model, we had some rough estimate how many training samples we needed, and it's like 500,000 commits for 2 test projects was our goal. On average, a commit touches around 10 files, which would be 15,000 nodes and around 100,000 edges. Processing this would take us multiple weeks. And even though we tuned Memgraph to its end, like we get loose of some consistency mechanisms, for example, we didn't care for non-repeatable reads and set it to read committed, because we are, even though planning to have a undercomplete static analyzer. Also, we tried our best to tune it to the end using indexing, but in the end, our problem was just not solvable. Like getting all paths, even just some 10,000 with this amount of nodes and edges, it's kind of overwhelming. So I kind of reformulated the problem a little. Instead of we want to identify whether a program is vulnerable, we want to identify whether a patch introduces a vulnerability to the program, which makes it the problem much more easily solvable, because instead of searching paths between some source and sink, we are now looking for a path between source and sinks intersecting changes that have been made in this patch, which like is much more easier to calculate than finding all source and sinks. So this was the kind of thing we tried to do, and it was actually fast. So yeah, our kind of method we came up with is called PAVUDI, Patch Vulnerability Discovery, kind of easy, and we called it our method interprocedural taint graphs, just like resembling the real taint analysis I've showed you in the fundamentals. We also use some kind of causal graph isomorphism network, which is a bit more sophisticated than the graph convolutional network I've shown you before. And we trained it on those paths for FFmpeg and QEMU, two very kind of large open source tools, C tools to be honest. The problem is we couldn't benchmark it because we kind of come up with this new like task, and before us, like in there were only vulnerability detectors for functions or slices. So we had to take those well-established machine learning models that detect vulnerabilities in files and functions and kind of aggregate their decision to the patch level, using, for example, the maximum of the decisions, the mean, the probability, and so on. So we compared it against 4 graph machine learning based static analyzers, 2 token based, and 1 heuristic one. And we had an around 50% increased performance against all of them, which is kind of interesting. That means that more context using like those taint path is actually important to rule out such false positives I've shown you in one of the first 3 slides. We also see that we are suffering less from concept drift. That means most of the models get worse, are sooner required to fine-tune or retrain than our model. Also, the number of touched methods within a commit is much less affecting the performance of PAVUDI than the other baselines. In the end, we developed an efficient path extractor, found 4 real vulnerabilities actually, and had a kind of promising approach for machine learning for static analysis. Yeah, if you want, you can read through the paper with the QR code on the right. But so far, that has been my talk. I hope you enjoyed it, and I'm happy to answer all of your questions.
Thank you, Tom. This was an amazing presentation. Thank you for sharing your work with us. Maybe just a comment on my side. You were talking about how you were choosing a graph database, but was there ever an option to choose another type of database, not a graph?
We thought about a relational database first, but that was too slow. We tried it even, and then we also tried just using like my first kind of attempt was using Python. I implemented this whole thing in Python without a graph database, and it was so slow, it was frustrating. Then I switched to Java, and then I had to look for a graph database that would fit my needs. Yeah.
Yeah, I mean, it makes sense because all of these deep path reversals that you're actually running in the background, then yeah, that's a really good use case for using graphs rather than a relational database.
That's true, and also Memgraph came with some interesting predefined or user-defined functions. I would say, for example, breadth first search was readily available. I didn't have to implement it myself, and we used it for our traverses, which was great.
Great. And how was your experience with Memgraph overall?
I loved it. I kind of loved the support. I didn't think I could have gotten a similar support from Neo4j. I kind of liked the UI because it was very like it gave me some kind of feedback loop. This UI, they could instantly try out to find vulnerabilities without having some kind of machine learning model on the back end.
Yeah, I get it. And what's next for you? Like for you done now this research and congrats on your PhD, but what's next for you?
Well, I'm still like I still admire graphs. I'm still a fan of graphs, and I hopefully can like do some more graph research at Amazon, maybe even
Mm-hmm.
with Memgraph, because we're working on network traffic, and I guess it would make sense to think in terms of graphs there as well. Yeah.
We have something related to that, a question from a viewer, as you are at Amazon, did you look at Neptune? That's a good question. But
Not yet, actually.
not yet, yeah. You recently joined Amazon, I guess, so it hasn't
I
been on
think
your radar.
I think I've seen a blog post about it. It's from the
Mhm.
AWS guys, right? If I remember correctly. But no, I haven't taken a deeper look into it.
Okay, that's cool. I mean, I like that you love Memgraph, so I do encourage you to try out Memgraph as well. We have another question from Deep. He's asking, are you running this in production? If not, what are the challenges of getting it to production?
Mm, let me think. Um, we tried it out with some productive code, but unfortunately, it was still too slow. Yeah, it's. I mean, this sounds now that it's not working or something like this, but
Hmm.
it's kind of like fundamental research, or more or less, to find new ideas. And well, what I just wanted to do here was to try to find some new problem statement to improve the lack of context in learning-based static analysis, and hopefully thinking about patches and not about state of the programs in their entirety opens up more research um, ground for machine learning based static analysis. This is
I,
especially important because if you think about LLMs are now used everywhere, and even they are lacking context. Like they have a
mhm.
limited context width.
And that's where graphs again are now interesting.
Yeah, everywhere graph.
Yeah, yeah, but I think, yeah, definitely your research contributed really well into this space. And as you said, like for anyone else who's left to contribute more and to continue doing stuff in that area.
Mm.
Another question is, what is the latency you need to make it viable to see it in production? What would you expect?
Hmm. I don't have concrete numbers, but I remember I had some self-written kind of versioning implementation in this Java code. And if I would step back a little from my implementation, I would say that this could be written better or more performant on top of on Git. Like Git is already having some kind of delta algorithm, so it was kind of an like a boilerplate for me, like an overload to write my own delta algorithm. So that's the thing I would improve, and then it could be production ready. But I have no concrete numbers in mind. And the code is of course open source. You can just have a look at it, and maybe you see what I mean.
Yeah, definitely. Everyone take a look at it. Like if it's on GitHub, start the repository as always. And yeah, I think that's it with the questions. Thank you, Tom, so much for presenting this, and thank you everyone who asked the questions. And yeah, I think that's it. I hope everyone enjoyed. I know you did. And hopefully, Tom, we'll get to see you on another community call for another research of yours. And I'm looking forward to hearing more about your progress within this area.
Thank you so much for having me.
No problem. See you all. Bye.
Bye.